Okay, well, let's get started. Hi, everyone. Welcome back to section. Before we get started, just a heads up, the midterm is in 6 days. So, do you have any questions about the midterm? Yes?
My laptop will not stay alive for 2 hours. Will it be enough charging? My laptop, we're just not gonna make it for 2 hours.
I encourage you to email like Tyler or Kate, and they can try to like find. They'll either they can either loan you a laptop or they'll find a way to make sure you sit next to an outlet. But typically, what happens at midterms is everybody wants to charge, and some people end up like doing the exam sitting on the floor next to an outlet, which is super uncomfortable. So I encourage you to email Tyler or Kate first, and then just to ask what can be done about it, and then just make sure it's done. Okay, yeah, because the worst thing that can happen is to go out of battery during the exam. Okay. Any other questions? Midterm? Yeah. Pointers will not come up. Oh yeah, that's a good point. So I forgot to do this in my last section, but let me write out the topics on the exam. It's pretty much going to look like this. So there's going to be a, let's see, there's 5 topics: algorithmic analysis, so big O, ADTs, recursion, backtracking. Okay, and also like a little like intro C++ thing. Okay, so kind of week 1, week 2, week 3, week 4. Okay, no pointers, no Today you learned about structs. Well, structs might appear on the exam, but you don't have to know the details of it. You just know how to use it. Okay, so do a little review of structs, but no pointers, no heap and stack stuff. Only these will be on the exam. Okay, and the exams almost always look something like, well, there's one right question. There's one read and one write for recursion. And there's probably like one read, one write, and probably like one read here. Okay, so you probably have to write 3, maybe 4 programs. Okay, these programs are small. They're like at most 30 lines long. So yeah. Also, you have 2 hours, and this is, I think all the questions are weighed the same. So spend some time on the read questions because they're relatively easier than the right questions, but you can't really get partial credit for those. So make sure you spend some time on the read questions. Okay? All right. Any other questions? I always get the question, can you use arm's length recursion on the exam? The answer is yes, because we don't grade on style, but it will make your life a little easier if you don't use arm's length recursion, probably. Now, if you can't think of anything else to do but to do arm's length recursion, then go ahead. Okay? Any other questions? Do we know when it is? 7 to 9 p.m. Okay, there's no lecture on that day. All right, let's get started then. So today we're going to talk about recursive backtracking. And before we go into that, I just want to do like a quick organization of like, I kind of want to classify the kinds of recursive backtracking questions you can find. And then what I often tell students is that even though it might seem daunting that there's so many different kinds of recursive backtracking questions, I have like a list of like 9 to 10 recursive backtracking questions, which after you've seen all of those, you pretty much know how to do any backtracking question. All right. At this point, when I see like a new recursive backtracking question, I think which one of those like 9 to 10 is most similar, and then just the solution also looks really similar. Okay. I'll write that list down later. You can look on code step by step. All the questions are there, and then you can try them yourselves. Okay. Basically, if you do all 9, 10 of them, and then you are really confident with them, you should be doing great on the backtracking question. Okay? All right, but before we get to that, I kind of want to classify these backtracking questions. So one kind of backtracking question you'll see, one distinction you'll find is permutations versus combinations and subsets. Okay? In recursive backtracking, you're always trying to build some sort of object, some sort of desired object that satisfies some constraint. So some examples you've done, build all binary strings, right? Build all binary strings which have exactly one of them. Okay, these are all like backtracking questions where you want to try to build some sort of object, and this object that you build, sometimes you do care about the order, sometimes you don't. Okay, most of the examples you did in lecture, you mostly cared about order, although there was like 1 or 2 questions you didn't care about order. The way you make choices, the choose, explore, unchoose, that choose step, is pretty different for permutations versus subset combination questions. Okay, so I just want to point that distinction out. What examples in class did the order of the thing you build matter? What are some examples from lecture? So as a hint, print binary strings, that was one of them, print binary. That was one example. Any other examples you remember? You did 3 days worth of examples. All right, one more, dice sum, where you had to write all possible sums of all possible dice rolls that sum into a certain number. That was one of them. Any other examples? Yeah. Yeah. Okay. Yeah. Yeah. Awesome. So escape maze and 8 queens. Yeah. So all those, the thing that you're trying to build, the order in which the objects are in that thing you build matter, right? For print binary, 1 0 0 is different from 0 1 0. Right? In dice sum, I think on the example you considered 6 1 1 to be different from 1 1 6. All right. So in those examples, we call those permutation questions. You didn't see too many examples where there wasn't, the order didn't matter, but does anyone remember one that didn't matter? Yes.
Subsets.
Yes, subsets. Yes, I think it called it sublist. So that was one of them. I think there was another one. I didn't know there was a second one until someone told me last section. Was there one called like guest list?
Wasn't that the same one?
Oh, that was the same one? Okay, fine. So sublist, guest list, yeah, those are the, in those, because you only care about who showed up, you don't care about what order they showed up, so that's a combination subset question, okay? And you'll recall that during lecture, Tyler mentioned that you built this tree using an inefficient method, and then you built it using an efficient method, and I want to point that distinction out, okay? So we'll look at an example of this later. The other thing I want to just quickly mention is, you notice I wrote 2 columns here, and the reason for that is this, we call these exhaustive search questions. And when we call these like true backtracking questions. Okay. On the exam, when they say backtracking, it could be either, but technically exhaustive search means try everything and give me the best answer. Backtracking is keep trying until you find an answer, then stop immediately. Right? In print binary, you print everything. You don't, even if you found a binary string, you just keep printing. But for 8 queens, once you find a solution, you stop immediately. Okay? The choose, explore, unchoose steps look slightly differently for these 2 as well. Okay? So I've drawn a quadrant. Today we will do a question called crack, which is we're trying to crack a password that falls into this category. And then we'll do a question called sum, can calculate sum, which is in this category. I don't think I saw any lecture examples in this category, but oftentimes because students only think about this one, so when one of these questions come up on the midterm, they screw it up really badly, okay? So make sure you know the difference. All right, any questions at this point? Okay, let's try an example. So we're gonna start with the 5th question. Let's move over here. We're going to start with the 5th question. So I'll start here, then I'll move here. All right. So you don't have to read the question. I'll explain it to you. Essentially, what the question does is you want to write a program called crack. So let me start over here. Bool crack. it takes in an int length. Okay, this length represents the longest length of the password, the longest possible length. So if length is 5, then your password can be 0, 1, 2, 3, or 4, or 5. Okay, letters long. Now, what we want to try to do is we want to try all possible passwords, all possible alphabetic passwords that are no longer than length long. Okay, and then we're given a function called login. So let me just write that here. We're given a function called login, which takes in a password and it returns true or false depending on if we successfully logged in. This is kind of similar to what was done during. This is similar to like how people actually try to hack passwords. If your password's like really short, then the bad thing that could happen is you can try to run what we're gonna write right now, and it might take like an hour, but it will try every possible login password and find the answer. Okay, that's also the reason why some sites prevent you from like, they only give you like 3 tries or something. Okay, so we're gonna write a program which actually tries all the passwords, and then when it finds that password, it stops, and it says, oh, here's the password. Okay, all right, let's try starting with that. So let's think about this as a recursive, as in like a recursive backtracking question. How are we building up this string? So we're gonna build up a password, which is gonna be a string, right? How are we building that string? And how's that related to like choosing? What exactly are we choosing here? Any ideas? Yes.
So you said it was all alphabetical characters?
Mm-hmm.
It's like choosing a letter from the alphabet.
Okay. So we have a bunch of letters we can choose from, A, B, C. I think the problem also wants us to try like uppercase, so let's also write the uppercase letters all the way down to Z. Okay, so we have a bunch of choices, and then how are we using these choices to build our password? So as a hint, we're gonna build a password that looks something like, I wanna make sure I do my space correctly. So a password which could have a lot of characters. And then what do you think a choose step would be? Suppose we started with this empty one. How can we try to extend the password? Yes?
Like, see, would it be a bit like the 8 queens, kind of like, and they, like you would choose the first one, and then you would try from all the second options, and then you try, and then if it doesn't, you'll backtrack back and try the next one, and then it works.
Yeah, exactly. Let's draw like a tree diagram for that, and then you can see how that works. So yeah, you're right. It's really similar to the 8 queens question. All right. So initially we start with an empty string. Oh, that's too large. Let me erase this. So initially start with an empty string, and then just like you mentioned, we try one of the choices. So we can say, okay, we're gonna, for the next letter, let's put the A in. Okay. Now, that's just one of the choices. What's another choice you could have done? Yeah, you can also do the B. You can also do any one of them up to Z. Okay? But first, let's just try, suppose we tried A. Okay? Now, A could possibly be a password. It could be a password. It's a bad password, but it could be. So you can try logging in with that, see if it works. If it doesn't work, then how can you try to build longer passwords using A? Mm-hmm. All right, let's try to make the choice again. What's one choice you could make? Yeah, you can make another A. So let me write out the choices. This is choosing A, B, up to Z. We choose another A here, in which case we can get AA. You can also try B, in which case we get AB, and so on. Okay. All these other choices, the same thing applies. You can also put A here, and then you get A. Oops. BA, BB. Okay? All right, and this, we can just continue this process, just build more and more layers. When do we have to stop? Yeah, exactly. So technically, you can continue this infinitely, but just for simplicity, let's stop it at some sort of length. So this is going to keep going until it reaches like a really long a really long password A. Don't exactly know how long it is. That's our parameter, but it has length. Okay, so once we reach this point, we stop. Okay, you might want to think about how that applies to our code. Okay, all right. So let's try to think about what we're going to do for the code. Let's write some pseudocode first. We always want to think about base case and recursive case. Recursive case. Okay. What base case can you think of? Yes. Okay, so if the length is 0, what happens if the length is 0? Okay, sure. Okay, we can make. Okay, yeah, we can make that a base case. So I assume that means you want to change this length. Sure. Yeah. Okay, we can do that. So let's just for the sake of simplicity, let's say the length was 3. Okay. So all right, then what your suggestion is every time we make a choice, we're saying, okay, now we want to add 2 more letters. Now we want to make 1 more letter, right? In which case, your base case would be. Your base case would be, okay, you have 0 letters. That means you can't go any further past that. Okay, so that's a base case. Let me write that down. If length is 0, then you want to stop something. Okay. Any other base cases? Could we possibly stop before we reach the bottom? Yeah. Okay. Awesome. So if we find that one that works, and we use the login function, right? If we find the one that works, so if login of the password is true, then that also works. Okay. Anyone want to explain why do you want to put this one before this one? Why might it be a good idea to put this one before that one?
So it could be that long.
Yeah, exactly. So if the length is 0, AAA is technically a valid password you could try. So we should try AAA first. And if that doesn't work, then we know that, we're done because we don't want to keep extending it anymore. So that's when we stop. Okay, I kind of drew the colors opposite, but this first one is kind of what we know as a success base case, where we tried something, it worked, now we can stop. So here you can just say return true. The green one, which is colored oppositely, but the green one is called the failure base case, in which case, we've reached the bottom of our tree. We don't want to keep going down in the tree. So here we return false. Question, yes?
In the code, would you put like the check to see if the password's correct in the recursive case?
That's a good question. So you're saying, should we put the login check in the recursive case? Okay. Let's get to that when we finish the code. Let's try moving it around, see what that happens. Yeah, that would be a little arm's length recursion because if you remember from last time, if you were here, I made you all say this. All recursion ends in a base case. Right? If you do that check in a recursive case, what happens is you're kind of like skipping over the recursive call rather than ending in a base case. Okay, we'll get to that when we actually write the full code. All right. So remember for the recursive case, we want to try to think of the 3 steps. What were the 3 steps? Choose, explore, and choose. Awesome. Okay. So choosing is when you start modifying your parameters so that it is essentially you're starting at one of these cases and you're deciding, okay, I'm going to move down to the next bubble by making one of these choices. Okay, let's first start by making that choice. What would the code look like to making a choice? What does making a choice mean in this diagram? Yes?
Adding that letter to password.
Okay, cool. So let's add letter, let's call it CH into password. Okay, so that's choose. Okay, and then after you've added a letter into password, second step.
Recursive.
Okay, so we make a recursive call. Let's see, recursive call, and then you would give it into the new password. What else do you want to? Do we have to change any other parameters? To think about that, look at what's happening when you go from one bubble to another bubble. That choose step, right? We've added that letter. Notice what else is changing. Yeah.
Me?
Yeah.
Just do length -1.
Yeah. So there's two ways you can do it, and I'm gonna show what that looks later. But this is directly modifying the parameter. What you can do is you can also, as you're passing it in, just pass in something a little different. That way you're not actually modifying the parameters. So for example, one thing I could do is I could say length minus minus. That would like decrease the length by 1. But what I can also do is instead of actually changing length, I'm just gonna pass in length -1. Okay? The nice thing is length doesn't actually change. We're just passing in length -1. Does that make sense? Okay. And technically, we don't actually have to change password. We can actually just pass in. We can actually just pass in a new password. But so that would be explore. And then last step. Remember what the last step is called? Unchoose. Where let's see, choose. You're trying to go down in a bubble. Explore everything underneath that bubble. And then unchoose when you're done with that, move back up. So you want to try to change your parameters back to what they were before. Right? In this example, we don't have to change the length because we never actually modified it, but we do have to like make sure our password is back. So we can say pass remove ch from password. Okay. All right, so we have a letter ch over here, but we never actually said how do you get ch. How can we choose a ch? Yes?
Could you have a for loop that goes through all the letters in the alphabet?
Yeah. That's a great suggestion. Let's see. So notice that this only applies to going down one bubble, but we want to try all possible bubbles we can go down. So we're gonna write a for loop. Okay, I'll get to the code later, but you all remember how to loop over an alphabet, right? Word letters, yeah, okay. So for each alphabetic letter ch. Okay, all right. Let's try to convert it into code. Should be a direct one-to-one. So crack. How should we get started? Yes.
Well, we can make a helper function that also inputs the password. Or like, so we like from that we would call a second one that like inputs, I guess, to start an empty string and then you add the letters to it.
Okay. Great. Yeah. So yeah, this is important. Where notice that we are trying to build a password here. So one of our parameters has to be like that password, but we don't actually have a password in the parameter we write. Remember, you can't change this parameter, but you are allowed to write a helper function. Okay. So let's just write a helper function. Can't move that board. Bool crack helper int length, and then we're also going to give it string password. Okay, and here we just say return whatever the helper returned. We give it the length, and then since we're starting with the empty string, we're just going to put empty string here. All right, let's see. Let's do the success-based case. What does the success-based case look like? Yes.
Login password.
Okay, if login password, then sure. Yeah, here we can just return true because apparently this function we don't actually have to find the password. We just have to find a password. Actually, let's modify this a little. Actually, okay. Let's make it so that we return a password. It's gonna make signifying this a little tougher. because then how do you signify you don't have a password, right? One thing you can try is you can return like, can we assume our password is not empty? Okay, let's make the assumption that we assume the password is not empty. Okay, the issue I have is, okay, let's suppose we wanted to return like the actual password, which is definitely probably more important, right? Then here we can just return the password. My only concern is in the second case where you're saying, okay, if length is 0, then how do you signify that you failed? So this is kind of tough because, oh sure, we could throw. Let's see. So be careful about throwing here, because if you throw something here, then that means like, okay, we've gone down, we reached this case, we haven't found the password. If you throw something here, then this would crash, but you actually want to keep trying everything else. Okay. If you wanted to write some like throw catch statements, that's fine. But is there any better way? Go ahead.
Okay, this might be like overly complicated, but like making a boolean, passing it in, and then by reference, and then changing the boolean that way.
Sure. Yeah. That's a good way. You could put a boolean here. What's probably a little nicer, because it looks more like backtracking, is you put the boolean here and you put the string there. So you put the string. Yeah, put the string in the out parameter. Yeah, that would work too. That's a little. Yeah. I don't want to change the code a little too much right now, but let's just assume the empty string can't be a password. Okay. Do you have another suggestion?
Yeah, empty string.
Yeah. So let's just return that, and then let's just assume the empty string is not a password. Okay. Yes. Return null. So null is kind of a weird thing in C++. Null is really just 0, and I'm not sure if you can return null here. When you get to pointers, you'll learn about null pointer, but null is kind of a little hard to return here. I'm not sure if you return null what the string would be, if it's even valid. I'm not sure. Okay, I'll get back to you on that one. You might be able to return null. I'm not super sure. Right? But for now, let's just assume you just return an empty string. Okay. By the way, I've seen this on assignments. Why can't you return this? Why can't you just return this? And then later check if you return this. Yes?
Oh, because it's possible that could be a password, right?
Yeah, this could technically be a password. I don't know why you would want this as a password, but this could technically be a password. So you want to make sure you don't return anything that could possibly be a password. I don't know, maybe empty string could be a password, but let's just, for the sake of simplicity, let's just assume it can't. Okay? But to SCPD students, we're kind of changing the problem a teeny little bit so that it returns the string. Okay? The original handout says return a Boolean, but it's more interesting to return a string. All right, let's do, how do you loop over all the characters? Word ladders, remember? All right, go ahead.
For ch equals a.
Okay, equals a.
Ch is less than or equal to c.
Mm-hmm.
And ch plus plus.
Awesome. H plus plus. Okay. All right. How do we add a letter to a password?
So, just one question, don't we have to take uppercase too?
Yeah, that's a good point. So it would be nice if we can just loop from lowercase directly into uppercase. Unfortunately, the ASCII numbers don't like completely line up. There's like stuff between the upper and lowercase. So what I'm gonna do is we're gonna like convert CH to uppercase as well, and then we're gonna try both. Okay. All right. How can we add a password? Add CH to the password. Go ahead. Yeah, go ahead.
Wouldn't it be easier instead of adding it and then couldn't you just do the recursive call and then inside the recursive call put the password and then do plus? That way you don't have to like unchoose it later.
Sure, yeah, that's a good suggestion. So let's just directly make the recursive call, crack helper. And then instead of actually changing like pass, let's just pass in, let's see, we're passing in length -1 and pass plus ch. So that just automatically adds the character to pass. Okay. The nice thing is if you don't actually change the password, then you don't have to undo it. Okay. So here we don't actually have to undo pass because we never changed it. Okay. Another thing we want to do is we can do crack helper. Okay. So this is one recursive call. Another recursive call we want to do is crack helper length -1. Okay. Now what I'm going to do here is weird. You don't have to understand it too much, but I just want to make sure we write compiling code. Static cast char of to low upper ch. Okay, so what this does is it just turns it into uppercase and makes sure it's a character. To upper is kind of weird in C++. It returns an int for some reason, so just cast it to one of them. Okay. All right, are we done? We don't need any unchoosing, so we're almost done. But there's one issue we do here. We have over here. So one thing to note is if this successfully found a password, it will return the password. But then what happens next? It found a password, but it's going to keep searching. Right? Remember in recursive backtracking, once you find the answer, you want to stop immediately. How do we get around that? We want it to stop immediately if it found a password.
Does it return it as a bool, the crack?
Currently, we're returning it as a string. So if it's the empty string, that means it didn't find a password. If it's not an empty string, that means it did find a password. Yes?
Empty string, or I guess, yeah, if not empty string break.
Okay. So if it's not an empty string, then you know that it is a password. But instead of break, because break just skips it here, but then if it did return not an empty string, so if this was successful, let's suppose this returned AAA, right? We want it to end up, the final one should return AAA. So you want to like pass it upwards again. Does that make sense? Yeah, once you find that this returns AAA, you want to keep passing it upwards so that this final one returns AAA. So I'm just gonna, if that happens, then you just pass it back up. Okay, this is kind of inconvenient. Let's string found is equal to that. If found is not equal to the empty string, then return found. So if we found the answer, then we just return it immediately. Same thing over here. Let's set found to this again. If found is not equal to empty string, then return found. Okay. We're missing one more thing. On the exam, this is worth 1 point. We need to return something down here. Right? What should we return over here? So after the for loop. So suppose the for loop ran, it didn't find anything. It didn't find anything. What should we return down here? We should return the empty string, right? Because if we reach this point, that means we've tried every single character. We've tried the upper and lower case, and none of them returned something other than the empty string. That means we didn't find anything in this case in some bubble. We didn't find anything extending from the bubble A, so nothing here works. We have to tell the function above, oh, we didn't find anything by sending the empty string. Okay? Any questions? All right, we have 15 minutes. Let's do one more example. And I want to do this example because this one is, the way of thinking about this example is slightly different from that one. So I want to quickly talk about that example, okay? All right, so let's do, I'm going to erase this. Let's do number 1. Let me just quickly explain it. Number one is essentially you're given a set. Well, not a set. You're given a vector. And I don't like the Fibonacci sequence example, so I'm going to come up with my own. 1, 2, 3, 5. Okay, and suppose let's just do 1, 2, 5. And suppose you're given a number which is 7. Okay. The question is, can we use any of these numbers, some of these numbers, to sum up to 7? All right. Is the answer yes or no? Yes, because 5 plus 7 is 7. 5 plus 2 is 7. Okay. Yeah. So this would be true. But something like I'll just write it out because this is a vector because we technically allow duplicates. But something like this, 5, this would be true. But if you took the same thing and you said, can I do 6, that would be false. Okay. Anything else? Any questions? Okay, so we're going to try to build something like this. Okay. If we used the same idea of the recursive tree, let's try writing that recursive tree and see what we get. So oftentimes what happens when you do problems like these is you'll keep track of 2 different collections. One's called choices. So these are like the choices you have. And then you have another one called chosen, which is the stuff you've chosen so far. So for example, here my choices are 1, 2, 5. So it's chosen and choices. My choices are 1, 2, 5. And at each recursive step, I could say, okay, I want to choose the 1. So I'm going to choose the 1, and then I remove the 1 from the choices because I can't choose it anymore. Okay? You'll often see the words choices and chosen. It's sometimes just helpful to have both of those. Okay, so if we were to draw a tree for that, what would that look like? So up here, we start with the chosen is empty, choices is 1, 2, 5, and our number is 7. Okay. What's something you can do at this step? So you know that the very top bubble looks like this. What are some choices you can make? I mean, if you did something similar to what we did before, you can say, okay, I can choose either the 1, the 2, or the 5, right? So let's just pretend those are our choices. So we can either have the 1, the 2, or the 5. So 6, 5, and 2. We chose, let's add more colors to this. We chose the 1, we chose the 2, and we chose the 5. And then our choices are now 2, 5, 1, 5, and 1, 2. Okay? And we can just keep this process, but I want to point something out, which is each one has 2 choices. I'm not going to write everything out, but I want to point out that this one, so 6, and then this is 1 with 2, because we've chosen 1 and 5, versus this one, where we've chosen 1 and 5. Oops, not 1 and 5, 5 and 1. All right, but you can hopefully see what I'm going for. Okay, what do you notice about these 2? Any ideas? What's similar about these 2?
They made the same choices, but in different order.
Yeah, we made the same choices. We made 1, 5, 1, 5, but we made them in different orders. Okay? Think about this question. This question is asking, we're trying to choose numbers which sum up to 7, right? Does the order in which we make the choices matter? We're just trying to show that, oh, we can sum up to 7, but it doesn't matter how we get, like in what order we get to 7, right? 1 plus 5 plus 2, or 1 and 5 versus 5 and 1. That doesn't matter. Okay, this is what I call one of these combination questions, where the order in which you're making the choices doesn't matter. And if you do something like that, you'll get a lot of repeats, which is kind of inefficient, right? These two are going to give you the exact same answer. These two are both going to say false because this sum is, well, because this sum is not going to work. Okay, but imagine you're having a lot of these repeats and you're like building the exact same tree over and over again. Okay. So for these combination questions, when the order doesn't matter, we don't want to make the choices based on, okay, which one to choose next. Because then the order in which you choose the choices are repeats. What's another way we can build the recursive tree? So this is bad. Good. What's another way we can build the recursive tree? And it just somehow reminds you of how you did sublist. So for sublist, remember, how did you build the sublist? You looked at each person one by one, and you decided, I want to include this person, or I don't want to include this person, right? Yes?
Why don't you remove them from the group once you use them, so that you don't get any permutation?
Yeah.
And you put them back.
Exactly. You looked at person to person, and then for each person you decided, okay, I either want to keep this person or don't want to keep this person. But after you made that choice, you just forget that person existed and you kept moving on. Okay? There won't be any repeats because once you've made a decision with the person, include or exclude, you're not going to back out of that decision. You're going to keep moving forward. So you won't get any repeats. Let me try drawing out that recursive tree. Okay? So kind of like in that example, for combination questions, rather than seeing these as choices that you have to choose from, you should be looking at it one by one. So you're going to start at the first one and decide, do I want to keep this one or do I not want to keep this one? So for example, let's draw that tree again. 7, 1, 2, 5. D. And your choices, which I'll mark in orange, are either exclude or include. Okay? And we only focus on the very first element. So if we exclude, then that means our sum doesn't change. It's still 7. But we excluded 1 and we're not going to think about 1 again. Versus if we choose include, then we include the 1. Okay, maybe I shouldn't have done that many colors. And then we still just forget about the 1. Okay? You commit to making a decision about 1, exclude it or include it. And after that, you forget it even existed. Okay? Because if you build the tree this way, so you get more includes, excludes, more includes, excludes. Notice that you'll never have a repeat because everything in this tree will be different from everything in this tree because everything here does not have a 1, everything here has a 1. Okay? This is how you want to think about permutation, about combination questions. That is the correct tree to think about for a combination question, include, exclude. Let me just write that again. Exclude, include, exclude, include. At this level, think about 1. And then after that level, you don't think about 1 anymore. At this level, you think about the 2. Okay? Does this make sense? All right, do you see how these recursive trees are different and why this one is preferable for combination questions? So you won't have any repeats. Okay? We don't cover a lot of these in lecture, but they appear on the midterm, so make sure you know how to distinguish between the two. Okay, we have 5 minutes. Let's write this code because it's pretty fast because we don't have a lot of choices here. Okay, All right, if we kept this recursive tree going, what happens eventually? Can some. Okay, so what happens eventually if this recursive tree keeps going? Yes.
Number of choices are gone, or like the green vector, there's nothing in it anymore.
Sure. So if choices is empty. Okay, so what happens if choices is empty? Okay, I'll just write one example. So suppose you have a 7, you have a 2 here. Let's just keep drawing one more level. You have a 7 here. Versus like here, you have a 5 here. Oops, used a 5, so you have a 0. Okay, I'm not going to do colors again, but notice that the green one is empty, and we've made choices. This one we made the choice 2 and 5. This one we made the choice something, nothing. Okay. So once we reach the base case, if empty, we have 2 possible cases, right? All right, what's one of the cases? What happened here? Yes.
The right sum.
Yeah. So we got the right sum. So if the sum is correct, or rather, if this number is 0, right? If the number is 0, so if the target is now 0, then we know that we succeeded. Return true. Okay. Otherwise, so what happens if the sum is not 0? Yeah.
Return false.
Yeah, then we failed, right? Okay. We can also add one more optimization, which is if at any point you get if at any point you reach 0, then you don't need to keep going, right? If you reach 0 at any point, even if you're not at the very end, you know you're done. Okay, does that make sense? So yeah, I really like this this green part if choices is empty, and that's what you'll usually see. You can optimize this a little more by removing this, and you can say, oh, if the target is 0 at any point, then that means we're done. Right? Even if the 0 appeared up here, then we know we're done. But if we're doing that, then we can't just use an else, because like, okay, this is not 0, but we still want it to keep going. So here, we want to do something like else if. How do we know that we failed? Either choices is empty, or almost out of time, so I want to move this forward a little bit. But when one of these numbers reaches negative, then that means, oh, you went past the sum, we can't go anymore. So, or if the target is less than 0. Okay. And then let's just quickly do the choose, explore, unchoose steps. What are we choosing?
The number from the choices.
The number we're going to include or exclude.
Yeah.
Right. Okay. So I'm just going to write it quickly. Int val is equal to choices 0, and we'll make sure we remove choices. So choices dot remove 0. Here's where we can make the 2 recursive calls. So we want to make a recursive call on this and that. So my bad.
It's just really small.
Choices. Else if choices is empty, or if target is less than 0. Okay. All right, we remove that one, and then we can make the recursive calls. Can sum of, let's see, can sum of, what? How are we changing the recursive calls? We can either exclude, in which case we don't change 7. So else we can just say target choices. And we can also have can sum target minus value choices. Okay? Let's just turn this into code really quickly. Bool can sum of a, let's target int, target vector and choices. Okay? One more thing, because it's a backtracking question, if we find an answer, we want to be done immediately, right? So you want to wrap this in an if statement. If either this one succeeded or if this one succeeded, then what? Return true. All right, but be careful. Before you do that, you have to remember to do this unchoose step. Right? You modified you modified choices a little, so you have to change it back. So this is the most common mistake I see on the exam, which is forgetting to change it back in this case. So here you want to say choices.insert. You want to insert at index 0. You want to insert value. Okay. If both of these succeeded, then you're done. Otherwise, you want to return false at the end, right? Okay. And just as and the same thing over here, we have to insert choices back. Insert 0 val. Okay. Cool. Let's see. If choices dot is empty or target is 0, return false. If target is 0, return true. All right. Any questions? Yes.
So when order doesn't matter, that's a good indicator that you're going to be doing like include, not include.
Yeah.
Okay, and not just move.
Yeah. Oftentimes, not always, but oftentimes if the thing you're trying to build is a set, then it's probably order doesn't matter. Okay. In this example, because we allow duplicate, like we can have choices can contain 2 ones, so we can't have a set, but order still doesn't matter here. Okay. I highly encourage you there's a question on Code Step by Step called is measurable. And there's another question called, I don't remember, what's the name? And there's another question called, make change. Make change. Okay. These are both combination questions where the order doesn't matter, but they're a little bit trickier. All right. A common question I get is, when do you use a for loop? The difference between combination and permutation questions is not a for loop. The difference is that the order does not matter. Now, oftentimes you'll use a for loop for a permutation question, because for a permutation question, it's easier to do a for loop over like all these choices. But for a combination question, it's usually just include or exclude, so you don't use a for loop. Okay? There are some exceptions. Make change is an exception, and you should go do this problem and see why you need a for loop there, because these 2 questions, even though they're combination questions, it's not just as simple as exclude and include. For is measurable, it's exclude or include left, include right. Okay, so these are just a little bit different, but it's the same idea applies. Order doesn't matter. Okay, all right. Thank you for coming. Good luck on the midterm, okay? Yeah.